go. All right, folks, can everybody hear me okay? See my screen? Anybody? Hello?
Yes,
All right,
we
rock and
see.
roll. All right, let's get started then. It's 3:01. Um, so let's see. I'll tell y'all later when more people are here. Let's get started on this exam. So I've looked at a few of y'all's work. First thing is, it says graph, right? So what I'm expecting to see is a graph, right? So let's do the first one by slope. No, we'll do intercept method. So the intercept method is where we find both the intercepts. So if we're going to graph, we're going to need one of these. Okay. So let's let x equal 0. So you can see easily that if we let x be 0, then 2y is equal to 3. If 2y is equal to 3, then y is equal to 3 halves. Okay. So 0, 3 halves is a solution. And this graph that we're going to draw over here, it's going to represent all of the solutions to this equation. This is just one solution. Let's see, 0, and I'll make each one of these a half. There we go, 0, 3 halves, okay? Now I need a second point, right? So the easiest one to find is, well, let's let y equal 0. If I let y be 0, then clearly x is equal to 3. So 3 is a solution. Okay, so 1, 2, 3. This is 3, 0. And then we draw a line. Okay, and then I might add, let's see, this would be at -1. This would be at -2. So we have a sense of scale horizontally and vertically. That's how I would do that problem, right? When you do your work on these exams, again, it's not just the answer, right? I could type this into Google, say graph, and then draw that, right? You want to show your work, right? And you want it to be legible and organized. Like y'all are going to be business majors, right? Present it as something that you would present to a client, okay? Not just, I don't want to see this, right? Here's what not to do. Let's see. And then a 0 and then and then just a 3 here, and then like maybe just 2 points. Like that, what is that? You know, I see a lot of this kind of stuff. Like, where's the train of thought? Right? It's just like, you know, pieces of a thought bubbling up from who knows what. And like, where's the line, right? There should be a line between the 2 points, right? The line represents all the solutions to this equation. This is just 2 solutions, and without any labels, I don't even know what those points are. They could be anything, right? So this is unacceptable, all right? Follow the model if you have to, right? Explain your thought process. Have a complete graph. Have your points labeled. Actually draw the line. Actually draw the graph. That's the instructions, right? If you do all this and you don't provide that, right? Follow the instructions, okay? So, I mean, not everybody's handwriting is beautiful, but try to make it legible. Try to write complete sentences, okay? So let's look at number 2 here. So this one up here, I did the intercept method. We call it that because we found the x-intercept and the y-intercept, meaning the point where our line crosses the x-axis. This is where it intersects the x-axis. This point is where it intercepts the y-axis. That's why it's called the intercept method. All right, this one I'm going to do the slope intercept method. Okay, now we want a graph, so we're going to need one of these. Okay, so these both have the word intercept in them. This one has the slope. Remember, slope intercept method means put it in this form. Here's your slope, and there's your y-intercept, right? You can see this is the intercept. If I let x be 0, then y is b, right? Wherever it is, this is 0b, okay? So what we need to do is get this in that form. So let's see. This equation is the same as if I subtracted 2x from both sides. And that's the same if I divided both sides by 3. Okay, so I could see here my slope is -2/3, which could also be written with the minus on the bottom. Okay, my b here is 1/3. So just looking at this information, which we get straight from that, I could see that if x is 0, y is 1/3. So I'm going to make each tick mark worth a third. This is 0, 1/3. This up here would be 1. This is a third. All right. So we have our y-intercept here, hence the term intercept. But now we can use our slope to get a bunch of different points. This says go down 2, go to the right 3. If I go down 1, 2, right, see each one of these is a third, right? So there's 1. I need to go down further. So 1, 2, 3, that's 1. Oh, let me get it on the tick marks at least here. So 1, 2, 3 tick marks. I've gone down 1. Need to go down 1, 2, 3 more. So there's 1, 2. So every 2 I go down, I have to go to the right 3. 1, 2, 3. So this is 3. So on this axis, every tick mark is worth a third. This tick mark axis, each one is worth 1. So this point right here is, let's see, if I was at a third, right? If I go down 2, where is this at? This would be -2/3, 3, 4, 5/3, -5/3, and my x coordinate is 3. Or I could look at this as go up 2, go to the left 3. Now it's hard for me to go up 2, all right, because I made each tick mark worth a third here. But anyhow, I got 2 points. That's all I need to make the line, okay? Something like that. All right, so that's funny. So I have this point labeled, which I got by looking at the B. And I got this point labeled, which I got by using the slope. And I went down 2 and to the right 3. Down 2, right 3. Okay. I could have got a point over here somewhere if I'd have gone up 2 and to the left 3. But that's kind of, I don't have enough room for that. So notice I've connected my statements here, right? This equals this, if and only if, this equals this, if and only if, this equals this. put it in the slope intercept form so I can easily see what my M is. I can easily see what my B is. Once I know what M and B is, I could simply draw the graph. Okay? So that's what I'm looking for when I ask you to graph. Okay? Now, depending on how you've decided, if you've made each tick mark worth 1 instead of a third, your graph might look different than mine. That's why it's important to label. Okay? So this is not what I'm looking for. Something like this, right? Or if you just do this, right, that's not enough. Right? So let's have a quiz. I want you to graph. Now, if you're typing your workout, it's really hard to draw a graph, right? It's easy to just write this on paper and take a snapshot and upload it, okay? All right, so here's 2 problems. We'll take 10 minutes. Well, we'll take 9 minutes. At 3:20, we will work these together. All right. So have at it. All right, folks, let's look at this quiz here. We have 9 of y'all present. I'm looking at your grades. I sent out an email or an email. If you're missing any daily quiz or exams, you need to get them in by noon tomorrow because I have to issue early progress reports. All right, and there's no reason to have any zeros this early in the semester, okay? Especially with the solutions already there in Canvas. So easy to just look at them, copy them down, and submit them, all right, to at least get half credit. All right, so if you have any zeros, all right, on the daily quizzes or exams, I'm going to have to issue a progress report on you, which I don't want to have to do. But it's way too early to start already having zeros for no reason. They're free points, right? If you can't take advantage of the free points, it takes such little effort, and I don't see you graduating college. Okay, so either turn in your work or drop out now and save yourself some money. Okay. All right, let's look at this quiz here. All right, graph, right? So we have to produce a graph. Remember, there's an infinite number of solutions to this equation, and each solution has an x and a y. There's 2 things, right? And there's an infinite number of these ordered pairs, and if we graph them all, it makes a line. That's what the line is. Okay. So if we do, let's see, for this one, you know what? I hate these fractions. Let's get rid of them, right? So I'm going to multiply everything by 6. That's what I'm going to do. Multiply this side by 6 and this side by 6. I'm going to put this over here, and I'm going to move my graph over. Yeah. Okay, so if I multiply everything by 6, 6 over 2 is 3. 6 over 4. Let's see, 6 wasn't the best number here, was it? 6 doesn't get rid of all the fractions. What's the smallest number that 6, 4, and 2 all divide into? 12. That's what I'm going for. 12 over 2 is 6. 12 over 4 is 3. Times 3 is 9. 12 over 6 is 2. Times 5 is 10. Okay, let's use that instead. Okay, right, this and this are logically equivalent. So we'll do the intercept method. Let x equal 0. If I let x be 0, then y would equal 10/9. Okay, so this is going to be a lousy thing. So if I make this 1, then, oh, I got it upside down, don't I? 10/9. 10 divided by 9. 10/9. So that'd be just a little bit above 1 here. So this is 0, 10/9. Okay. And 0, 10/9 is a solution. And if I let y be 0. All right, that's gone. Then x is 10/6, right? Which we could simplify. If we divide the top and the bottom by 2, that'll be 5/3, right? And 5/3 is like, what, 1 2/3? Yeah. So 5/3, right? That's my x value. And 0 is a solution. So let's graph that. If I make this just worth 1, 5/3 is over here near 2. It's right about here, right? So this point here is 5/3, 0. So those are my two intercepts. I can draw my line through them. Okay, and again, this blue line represents all the solutions to this equation. If I could pick any point on that line, the x and the y, if I plugged it in here, this equation would hold, okay? So there's the first one. We used the intercept method. Let's look at this one here. We want to graph this guy. Well, there are no y values, right? So that's kind of awkward, but that's okay. I could, if I divide both sides by 3, this is the same thing as saying x equals 2. Well, that's easy right here, 1, 2. Every single point on this vertical line has an x value equal to 2. Like this point here, this is 2, 2. This point here is 2 minus 1. This point right here is 2, 0. Okay, and I might want to label a couple of tick marks over here on my axis, which I forgot to do up here. See, this would be -2, -2. All right. I mean, I can tell from this what the sense of scale is horizontally and vertically, but it's nice to have something separate from that that's just clear, right? This shows each tick mark is worth 1, right? If I didn't label this point, if I just had this tick mark here and this dot, if I didn't have this, I had no idea where this point is. I just know it's somewhere over 1, okay? So if you don't label your points, you haven't graphed the line. You just gave me something rough, you know? I mean, this isn't a computer printout, but it's the most accurate I can give you using, you know, my hands, all right, and a pencil. All right, so there's your quiz. Y'all have any questions? Okay. So we are now starting 4.1. So you should have finished your MyMathLab 1.1 and 1.2 and started 4.1 and 5.1, okay? Let's see where. Let's see where our schedule says we're supposed to be today. Remember, your schedule is here, the file, along with the lecture notes and the solutions to the past quizzes and exams. So today is what, February 2nd? So yeah, we should be on par here. So this week, 4.1 and 5.1, that's where we're at. All right, so 4.1, we're going to deal with systems of linear equations and two variables. What this is like, if I give you two equations with two variables, well, think about it. But this thing here has an infinite number of solutions. Let's say that's them. This one here also has an infinite number of solutions, okay? Now, the only place where both of these are true is where these lines intersect, okay? And this is what satisfies both of these at the same time, all right? Here's some solutions, here's some solutions. This point is the only point that solves both of these equations. Now you will also have situations where these are the same line, right? Where here's one line and the other line is the same line, in which case there's an infinite number of solutions to the two equations. Or you could have, here's one set of solutions, here's the other. If these lines are parallel, there may be no solutions that satisfy both of them at the same time. All right, so that's what's going on visually, or graphically, I should say. They call it a system of linear equations because there's more than one, right? It's a system. There's two of them. You could have 3 or 4 or 5. But the thing is, if there's 2 unknowns, you need 2 independent equations to get a unique solution. If there's 3 unknowns in x, y, and z, you would need 3 equations to get a unique solution. Okay? And they're called linear because each one of these is just a straight line if we graph them. Okay? And so there's a couple of tricks here. Like, how do I figure it out? One thing you could do is graph this, and just eyeball the graph, right? But that might be hard to do, right? We want to be able to do it mathematically to solve for an exact answer. So that's what we're going to learn how to do. So here's just a generic definition. I'm saying if you have, look, each of these has an x and a y, an x and a y. The a, b, h, c, d, k, those are all just numbers. All right, they're just saying 2 linear equations, just like these. Okay, that's all that's saying there. We can solve this. We're going to have 3 different methods. Graphing, like I just said, you could graph the 2 lines and look where they cross. Substitution, all right, that's where we substitute one equation into the other to get a new equation that only has one variable. And elimination by addition, okay? So 3 different methods that we can do to solve these. I hope I remembered to hit record. Yeah, I did. Okay. Look at these 2. All right. We could graph them and look at where they intersect, right? Let's do something else. We're going to do substitution here. All right. What I'm going to do is I'm going to rewrite this guy. I'm going to say y is 32 minus 2x. I'm just moving the 2x over here. So now that I know what y is in terms of x, I'm going to take this y right here and I'm going to replace it with that. And if I do that, I'm going to again end up with, again, I'm replacing the y value with 32 minus 2x. So this is a brand new equation right here. I got it by substituting one of these into the other. But this equation only has x in it. There are no y's. So I can just solve for x, all right? Substituting, we get this guy. All right, there's only an x. Now we can solve for x. So if we solve for x, let's see, this thing is the same as, if I multiply the 3 out, what is that, 96? 3 times 2 is 6. Let's combine some like terms. Those give us a minus 5x. 26 minus 96 is negative 70. Multiply both sides by a minus. 70 divided by 5 is 14. All right, I know what x is. Now that I know what x is, I can plug it in right there to get my corresponding y. So this is 32 minus 2 times 14, or 32 minus 28, or 4. So the solution here is 14, 4. And I can check my work. Let's check. First equation. If I replace the x with a 14 and the y with a 4, I'm going to get 28 plus 4, which is 32. which is the other end of the equation, and I have to check the other one as well. If I replace the x with 14 and the y with 4, I get 14 plus 12, which is 26. Right. I'm supposed to get 36 here, right? 3 times 4 is 12. 4, that's 26. I need to get 36. I did something wrong here. Right? This is 14 plus 3 times 4. So this isn't working. I made a mistake. All right. And it's good that we have this, because even though these numbers satisfy the first equation, that's not good enough. They have to satisfy both of them. All right. 14 plus 12 is not 36. Let's try it again. All right, so I have y is 32 minus 2x, right? And if I substitute that in here, I'm going to get x plus 3 times 32 minus 2x equals 36. So x3, this would be 96, right? Yeah, minus 6x, 36. Combining like terms, 36 minus 96 is negative 60. So x should equal 12. That's not the same as we got last time. Plug that in over here. 32 minus 2 times 12. 32 minus 24 is 8. So 12, 8 should be our solution. So let's check. So for the first one, if I replace x with 12 and y with 8, I get 24 plus 8, which is 32. Satisfies the first one. Look at the second equation. X plus 3 times y. 12 plus 24 is 36, which is what it should be. So this is good. All right, 12, 8. 14, 4 didn't work. It only satisfied the first equation, meaning if I graph this, wherever it is, this point lied on this line here, but it didn't lie on this line, okay? So this point, 12, 8, if I graphed both of these, this is the point where those lines cross. It is the one unique solution for both equations, okay? If we graph these, let's see, y equals 32 minus 2x is the first one. 32 minus 2x. 32 minus 2x. There it is. And let's look at the other one. This guy, the second one, I need to put it into functional form. Let's see, I would have a 3y equals 36 minus x. Divide both sides by 3. 36 divided by 3 is 12. So I have 12 minus x over 3 is the second one. 12 minus x over 3. 12 minus x over x over 3. Boom. See where they cross over here? Okay, it should be at 12, 8. You can look at it and see 12, 8. That's where they cross. Okay, so these are the solutions for each of those separate equations. This is the only point that's a solution to both equations. Okay, so that's using substitution. I found out what y is in terms of x, and then I replaced the y with an expression with x. That way, I had a new equation that only has x's in it. There are no y's. And then I could solve for x. Once I know what x is, I plug it in, and I know what y is. Okay. So substitution, that's easy. Oh, here's a nice picture. Okay, and they did the whole check and everything. Let's do a match problem. Solve by graphing and check. Okay, so we're going to do this one by substitution again. So let's see. I'm going to substitute this one into that one. Simply because the x is by itself, I can easily say, okay, x is -4 minus 2y. And then I'm going to replace that x with this. And that's going to give me 2, the -4 minus 2y minus y equals -3. Substituting that in, all I have is the letter y. There's no x. So I can solve for x. We have a -8 minus 4y minus y equals -3. Combining like terms, I have a -5y. Add 8 to both sides. That gives me 5. That means y is -1. If I substitute that in right here, I'm going to get a -4 minus 2 times a -1. The -4 plus 2, which is -2. So, sorry, that's x, right? X equals, this is my x. So, -2 minus 1 is my solution. And I could check my work. Let's check. All right, first equation. If I replace x with a -2 and y with a -1, I got a -4 plus 1, which is -3, which is what I wanted. Now for the other equation, if I replace x with a -2 and y with a -1, I got a -2 minus 2, which is -4, which is what I wanted. So the answer is correct. Okay. Now if we want to graph these, I could graph them. We're going to use the software real quick. All right. To do that, I need to get the y by itself. All right, so this one would be, let's see, -y equals -3 minus 2x, or y equals 3 minus 2x. So let's graph this first one, 3 minus 2x. Take the equation, 3 minus 2x. Now let's see what the second equation needs to be. To graph this, I need to get the y by itself. So I'm going to go over here and be like, 2y equals -4 minus x. Divide everything by 2. 4 divided by 2 is 2, and then so -2 minus x over 2. -2 minus x over 2. -2 minus x over 2. Boom. Now let's see where the graphs cross. So here is my graph. All right. Do they cross at -2 minus 1? That doesn't look right at all. Right? Something's wrong with my graph here. This is where they should be crossing. -2 minus 1. They should be crossing over here. So something wrong. Again, let's check our work. If I'm going to get y by itself, I have a -y. If I move the 2x over, I get that. Multiply everything by a minus, so I get a 3 plus 2x. Is that my first line? No, I put 3 minus 2x. It should be 3 plus 2x. There. That looks better. Delete that guy. Those dots. There we go. This looks about right. 1, 2, and then -1. My point is at -2, -1. That's where the two lines intersect. That's where both equations are satisfied. Okay. Any questions? So that one was also done by substitution. We checked our work by graphing. Okay. Example 2, I guess this one they're just going to graph. Okay. Okay, so A, they graph it, and then, well, they just graph these two lines and look at see whether they intersect. 4, 1. You replace x with 4 and a 2 with a 1. 4 minus 2 is 2. All right. And here, 4 and a 1, 4 plus 1 is 5. So it works, right? And you can graph these however you want, right? I just plugged it into software, right? Because if we did this, with our, say, intercept method, I would know what this point is, and I would know what this point is. And then for the other line, I would know what this point is and this point is. And if all I had labeled was those 2 points and these 2 points, it might not be easy to look at your drawing and see and know that that point is 4, 1. Okay. Now on software, you can trace it. It'll allow you to move your little dot around. It'll tell you what it is. Okay. But a hand drawing, if your drawing isn't very good, it might be hard to tell exactly what that point is. Okay. These guys here, if you graph them, they happen to be parallel. So there is no solution to this guy. Let me show you why. So part B, let's put these both in slope intercept form. Let's see, if I subtracted x from both sides and then divide both sides by 2, I have that. Let's do the same for this one, put it in slope intercept form. I would have, if I subtracted 2x from both sides, I'd have this. Now divide both sides by 4. 2 over 4 is a half. 8 divided by 4 is 2. So for these, look at their slopes. They have the same slope. They're both going downhill at the same rate, a slope of 1/2 down, negative 1/2. They have different intercepts. One's at +2 and the other one's at -2, but they have the same slopes. So there is no solutions, right? There's nowhere that these lines intersect. These happen to be the exact same line. Look at this guy. If I divided everything by 2, I would get x plus 2y plus 4. That's the same equation. I just multiplied everything by 2. All right. If they're the same line, then there's an infinite number of solutions. Every single point on this line will satisfy both equations because the equations are the same equation. So there's an infinite number of solutions. So you either have one, none, or an infinite number. Okay, those are the 3 possibilities here. Okay, let's look at this matched problem number 2 here. Okay, solve them by graphing. Okay, well, let's see, A here. This is the same thing as y equals negative x plus 4. If I was going to graph that, my y-intercept is 4, and my slope is -1, right? -1. That's the same thing as -1 over 1 or 1 over -1. That means go down 1 to the right 1, down 1 to the right 1. Or up 1 to the left 1, up 1 to the left 1. Down 1, right 1, down 1, right 1, down 1, right 1. Okay. So there's my first line. What about my second one? I'll do it in dark blue here. Let's see, I would have minus y if I subtracted my 2x from both sides. Divide everything by, multiply by a minus. I get 2x minus 2. So my b here is -2, and my m is 2, or 2 over 1, which could also be written as -2 over -1. These are all just 2, which is my slope. First off, my b is -2. And now my slope says for every 2 I go up, go to the right one. Up 2, right 1. Up 2, right 1. Up 2, right 1. So this point right here, which looks like 1, 2, 1, 2, all right, that should be the point that satisfies both of these. Let's check. 2 plus 2 equals 4, right? 2 times 2 is 4, minus 2, well, is 2. So yeah, that's it. Okay. Now for part B, I bet you these are going to be parallel, just because that's what they did up here, right? They had one that was parallel and then the same. So let's put this guy in slope intercept form, because they want us to solve them by graphing. So we need to graph them. So part B here, the first one, if I move my x's over, I get this. If I multiply everything by, or divide by a -3, 6 over 3 is 2, 9 over 3 is 3. So my b is -3, and my m is 2. So what does this thing look like? -3, 2, so I got to go down 1, 2, 3. I guess I'll make this like light blue here. All right, slope is 2, which is 2 over 1, or -2 over -1. This says go up 2, go to the right 1. Up 2, right 1. Up 2, right 1. Up 2, right 1. So there's the solutions to my first equation. Let's look at the second one. This one would be, I'd move my x's over and then multiply everything by a minus. All right, looking at this, okay, this is exactly the same as this. So these are the same line, all right? Yeah, they have the same slope, but they also have the same y-intercept. So there's an infinite number of solutions, okay? Any of these would work. So this one is what, a -3, no, 0 -3. Check it out. If I plug in a 0 here and a -3 there, -3 times -3 is 9. Look at the second one. If I put a 0 for x and a -3 here, a -3 is 3. So yeah, this point works. What's this point? 2, 1. Try that. If I replace the x with a 2 and the y with 1, this is 12 minus 3. That's 9. I replace this with a 2 and a 1. 4 minus 1 is 3. So this point also works. Again, every single point on this line is going to work. There's an infinite number of solutions because these are just the same equation, right? If I divide this, and this, if I just simply divided everything by 3, I get exactly the other equation. These are logically equivalent. So this one, I'm guessing, is going to be the one where they're parallel. All right, so let's look at part C here. The first one, I would get, if I move my x's over, then multiply everything with a minus. All right, if I'm going to graph that one, all right, my b is -4. I'll make this blue. My slope is 2, right? This is the same thing as 2 over 1 or -2 over -1. So I can go up 2, right 1, 2, right 1, up 2, right 1, up 2, right 1. There's my first one. Let's look at this second guy here. If I move all of my x's to the right-hand side, now divide everything by a -3, I get this. So I need to go up 6, 1, 2, 3, 4, 5, 6. All right there. And my slope is 2, same as this one. So I could say up to right 1. I'm going to look at this one instead. I'm going to go down 2, left 1, down 2, left 1, down 2, left 1, down 2, left 1. See, these two lines are parallel. they both have a slope of 2. They have different y-intercepts. One intercepts down here, one intercepts up there. They're parallel, so there are no solutions. None that satisfy the whole system. All right. And this isn't what I'm looking for you to turn in on an exam, right? This is me trying to present the concepts as fast as I possibly can because time is so limited, right? You need to turn in work that looks like this, right? Legible, clear, organized, etc. Not this. You wouldn't show this to a client, right? Okay, let's see. Where were we? That was number 2. Here's a long paragraph. System of linear equations is consistent if it has one or more solutions and inconsistent if no solutions exist. This is vocabulary, right? So inconsistent, consistent. Okay. A consistent system is said to be independent if it has exactly one solution, or dependent if it has more than one solution. So these have solutions, so they're both called consistent. This one's called independent, and this one's called dependent. And the reason why this is called independent is because this line and this line are 2 independent equations. These are not the same equations. These 2 lines, these 2 equations, they're the same equation. So they, in a way, you're saying one depends on the other, right? This equation is the same as that one. So they're dependent upon one another. They're the same. Whatever one is, the other one has to be the same one. So that's just some vocabulary they throw around. And here's just more of the same. The equations can either have one solution, no solutions, or an infinite number of solutions, right? There's one solution, it's consistent, and they're independent. There's no solution at all, it's inconsistent. There's infinitely many solutions, it's both consistent, and the equations depend upon one another, right? So this is the one where the lines are the same, right? This one is where the lines are different and intersect. And this one is where the lines are parallel. There we go. In the past, one drawback to solving systems by graphing was the inaccuracy of hand-drawn graphs. Graphing calculators have changed that. Graphical solutions on a graphing calculator provide an accurate approximation of the solution to a system of linear equations. Right? So the graphing does not give you an exact answer, right? It's just an approximation, especially if you're using a graphing calculator, right? We have computers now. You can see that. I mean, if you're doing business and you're talking about millions of dollars, you don't want to just be close to a few decimal places. You want to have things exact, especially if there's things that are using this information over and over and over again. So on a graphing calculator, you'd look at that and be like, okay, what's this point? Oh, I don't know. It's too small to even read. Now you can it'll allow you to trace this line, meaning you can put a point on there and drag it, and then it tells you what the points are, right? Well, I mean, that's better than the old hand-drawn method, but it still sucks. These are not exact answers. These are rounded to 2 decimal places, right? So if these are in millions of dollars, right, I'm not comfortable with just saying, oh, it's $2.6 million. What about the rest of it? Substitution. All right, we already talked about that. We used it to find exact solutions. All right, that's the key here. Exact solutions. That's what we want. Exact. Okay. So, and I showed you up here what to do. You substitute one equation into the other to get a new equation with only one variable. There we go. So if I was looking at this, two equations, two unknowns, there should be a unique solution. These both have an x and a y in it. So I'm going to just say here y, if I subtract the 5x from both sides, I get this. Now I'm going to take this guy and put it right there. That's going to give me, replacing the y with a 5x plus 4. This equation I made from these two, and there's only one variable. So I could solve for x. I multiply the 3. 3 times 5 is 15. 3 times 4 is 12. Combining like terms. All right, those give me 17. If I add 12 to both sides, I get that. So x is 1. Now I know what x is. I could put it right there and find out what y is. 9. That's my y value. Y equals. This is chain equality. So 1, 9 is the unique solution. There's only one solution. We could check. All right, for the first equation, if I replace x with 1 and y with 9, I get 14. And that's not any good. I need to be getting 4. Right? So I did something wrong. This did not work. Let's check our work here. If I move the 5x over, I get that. If I substitute that in, I have 2x. 2x minus 3 times a minus 5x plus 4. Multiplying this out, that gives me a positive 15, a positive 12. 2 and 15 give me 17. Adding 12 to both sides, yeah, x should be 1. And then up here, if I forgot my minus 5 here. It's minus 5 times 1. Minus 5 plus 4 would be minus 1. Well, this should be a minus 1. So let's check our work. 5, it says 1 minus 1. So 5 times 1 plus a negative 1, that gives me 4, which is what I wanted. Now for the next equation, 2 times 1 minus 3 times a minus 1. It gives me 3 plus 2, which is 5, which is what I wanted. There we go. Now we can box our answer with red ink. Okay. So that's how you do substitution. Solve for one variable, substitute that into the other one. That gives you a new equation that's a combination of the two, but there's only one variable in it, so you can solve for one of the variables. Once you know what one of them is, you can substitute this into either one of these to get your y value. I always pick this one because the y is already by itself, so all I have to do is replace the x. It's just faster. All right, matched problem number 4. Okay, I'm going to substitute one into the other. I'll use this one here. I have a minus y. If I move my x's over, multiply everything by a minus. Now I'm going to take this, and I'm going to replace that with that. So substituting, I get 3x plus 2, replace the y with this, and that's equal to minus 2. There we go. Now we can solve for x. So that gives me a 3x plus 4x plus 12. Combine our like terms. 3 and 4 makes 7. 12 minus 12 is 0. So x has to be 0. If I substitute that in, I'm going to get 6. So 0, 6, right, is my solution. Let's check, make sure they work. 0, 6, 3 times 0 plus 2 times 6 is 12. No, I need a minus 2. So I screwed this one up as well. Let's check our work. All right, if I move the 2x over, I get this, multiply everything by a minus. That looks good. So now I'm using this guy, 3x plus 2, replacing y with a 2x plus 6. So I have a 3x, a 4x, 2 times 6 is 12. It's supposed to be a minus 2 here. I copied that down wrong. So combining 3 and 4 makes 7. Negative 2 minus 12 is negative 14. So x should be minus 2. So if I replace x with a minus 2, I get 2 times minus 2 plus 6 minus 4 plus 6, which is 2. So I have a minus 2 and a positive 2 for my solution. Now we can check our work. Check again. So the first one, if I replace x with a minus 2 and y with a positive 2, I got a minus 6 plus 4, which is minus 2. And now let's check the second one. Replace that x there with minus 2. And we'll replace the y with a positive 2. I got a minus 4 minus 2, which is minus 6. That means that's the correct answer. So it's 4:06. Let's take a 10-minute break till 4:15, basically. Break. Resume at 4:11. No, that's not right. 4:16. There we go. 10-minute break. And then we'll knock out this section. All right, class, we're back. About that, I got lost in a long email. All right, so where were we? I need to record. All right, we are recording. Elimination by addition. Okay. Substitution will always work. Okay. What is this? Let's do example 4. Instead of substitution, we're going to do elimination. All right. So instead of substituting one into the other to get a new equation that only has one variable in it, what we could do is add these two equations together to make a new one, or I could subtract them to make a new one. Like, for instance, let's say I just keep this guy the same. And if I multiply everything here by 2, I get this guy, right? So this is the same as this. I just multiplied everything by 2, okay? Now that doesn't help yet, but what I can do is I'm going to add these equations together. It's not an X, it's a plus sign. If I add these, and the reason why I multiplied everything by 2 was so that this would match up. That way, when I add these, I'm going to get 7x. Those cancel out, and then I get a minus 14. Okay? So you can see right away that x is minus 2. Okay, so it's a different method. We're still getting a new equation by combining the old two, right? But instead of substituting, we're adding these two equations together to get a new equation. And of course, once you have your x, plug it into either one of these equations and you can get your y, right? If I plug this in here, I got 2 times minus 2 minus y equals minus 6. Or if I add 4 to both sides, I see that y equals 2. Okay, so that's elimination by addition, right? I added these two equations together to eliminate, in this case, the y value, okay? And again, I had to double everything here so that those would match up. They're equal and opposite. That way, if I add these and these and these, the y's go away. So that's a different approach, right? And that might be easier. But substitution, I mean, it's easy, but this elimination by addition, you can almost do it in your head. You look at these and be like, man, if this was just twice that, right? If I doubled everything, those would match up. So I could be like, okay, 3 plus twice this is this. This plus twice that goes away. And minus 2 plus twice that is minus 14, right? So you might find it easier to do elimination by addition instead of substitution. It's just an alternative approach, okay? So what they're saying here in this theorem, let's see what they're saying. What are they saying? Samantha, that's fine, Samantha. Take off if you need to. All right, you can watch the video on YouTube later if you need to, okay? And don't forget your exam. All right, you can get it out of the notes. So a system of linear equations is transformed into an equivalent system if two equations are interchanged. Okay, I can switch these. Okay, fine. It's still the same system. An equation is multiplied by a non-zero constant. Okay, I'm like right here, I multiplied everything by 2. So I got that. So this system is the same as this system. All I did was multiply everything in the second equation by 2. A constant multiple of one equation is added to another equation. Okay, well, we took a constant multiple of this, namely 2, to get that, and then we added these to get that. So what's going on here, basically, as we do this stuff, right? We start off with these equations, and we ended up with 2 new ones, namely x equals minus 2 and y equals 2. So instead of these, we just turned them into these. These are 2 equations. They just happen to tell you exactly what x and y is. So here's how it goes down. Basically, you start off and you have something like this and this, okay? And then you end up with something like, see this point right here? That point never changes. That point never changes. What is that? It's right about here. We end up with this and this, right? X equals 2 and y equals 2, or whatever the numbers were, I forget, right? So this is like some, funky line. This is some funky line. So we replace one of these lines. So by replacing one of the equations, like this line might stay the same, okay? But we're going to take the equation for this line and we replace it with this line. And then when we take this equation and we replace it, right, we'll replace it with this line. Here, let me, I guess, color code these. I'm going to make this one green. Green. It's still green. Okay. So we replace this line with this one, and then we replace this line with that one. All right, so these had two nasty equations. So like up here, we had two nasty equations. These are just two couple of curved or diagonal lines, right? Like this and this, right? When we added these together, we were going to basically get rid of this one. So we're keeping that one and this one. So we got rid of this line and turned it into x equals 2. Boop. So we still had this guy and this guy. So when we substitute this in here, we ended up with this, right? When we put that in there, this turns into that one. So we simplify it. So then we get rid of this guy and turn it into that. But that point where they intersect never changed. That point is the solution, right? It's what solves both the lines. So the lines may change, the equations may change, but we'd rather have this than, 2x plus 3y equals 1 and, x minus 2y equals 4. These suck, right? I'd rather have it written down like this. Tell me exactly what x and y is, right? These two equations, and I'm just guessing here. I'm just putting something like, I'm putting random equations down, but these two are logically equivalent to these two because they have the same solution. That's what's going on behind the scenes. Okay. So let's look at another example here. And I know like I'm not writing things pretty and all, but if you want to see it all pretty and step by step, read the book. That's what the book is for. Right? If I sat here and just wrote down what the book wrote down and said what the book said, there would be no point in me being here. So here we go. We have these two guys. I want to do elimination by addition. Well, if I add these, I'm not going to get rid of the x's. If I add these, I'm not going to get rid of the y's. So what I'm going to do is if I multiply everything here by 5, I multiply everything here by 2, I'm going to get a new set of equations. I will get 15x minus 10y equals 40. And this one would become 4x plus 10y equals minus 2. All right. Really, these are logically equivalent. All I did was multiply everything by 5. So this equation is exactly the same as this one. The lines are exactly the same. And the reason why I did that is I can now add these. If I do that, I'm going to get 19x. The y's go away, and I get 38. And that's the same thing as saying what x equals 2. So I started off with 3x minus 2y equals 8. 2x plus 5y equals minus 1. That was my system. I multiplied everything by 5 on the top and everything by 2 on the bottom, and I got a new system. But they're logically equivalent. In fact, these are exactly the same lines. Okay. But then I added them together. And basically, I'm keeping the first one, but I'm replacing this guy with the new ones. Let me move this down. Boop. So the bottom one is getting replaced with x equals 2. Okay. Now I know what x is. I can simply replace x. So this turns into, if I replace x, I would have 15 times 2 minus 10y equals 40, or minus 10y. 40 minus 30 is 10, or y equals minus 1. So now I'm going to replace that with y equals minus 1 and x equals 2. So my solution is 2 minus 1, okay? So I started off with 2 equations, and I ended up with 2 equations. It's just these are written much more clear to a human than those, right? These are 2 different lines than these 2 lines. They're not the same lines, but these intersect in the same places that these intersect. Okay. Now, of course, we could check your work. It's possible I made a arithmetic mistake somewhere, but you get the process here. Okay. Look at another one. So enough of the philosophy. Let's just focus on getting the answer here, right? That's what y'all want to be able to do. Just show me how to get the answer. Well, I want to be able to add one to the other so that one of the variables goes away. If I multiply everything here by, let's see, 2, I'm going to get 10x minus 4y equals 24. And if I multiply everything here by a minus 5, I'm going to get a minus 10x minus 15y equals minus 5. And if I add these, the x's go away. I get a negative 19y equals 19, which tells me that y equals minus 1. Once I know what y is, I can plug it into either equation and get what x is. Let's plug it into this one. 2x plus 3 times a minus 1 equals 1. So 1 plus 3 is 4. So x equals 2. So boom, 2 minus 1. There's my answer. Pretty quick, right? So sometimes substitution might be quicker. Sometimes elimination might be quicker. They both work. Two completely different methods. All right, this is something we do a lot. So, oh, here's this long ass paragraph. All right, let's put it in the notes and we'll skim it. All right. I try to avoid long paragraphs. All right, so here's two equations. Is this the same two we just did? No, two different equations. Okay. So we're looking at whether it has no solution or infinitely many solutions. Okay. Well, if we double this guy, we get this. Then if we add them, the x's and the y's go away. See that? And we get 0 equals minus 7. That's never the case. So this is no solutions. All right. This means that the two lines never intersect. All right. It means they are, in this case, check it out. If I multiply everything by 2, all right, they're a lot alike. They are parallel. They never cross. Okay. Now let's look at this set here. Okay. If I try to do elimination, if I multiply everything here by 2, I'm going to get a 2x, a minus a y, and 8. If I add these, those go away, and these go away, and those cancel, but I get 0 equals 0. 0 is always equal to 0. So that means there's an infinite number of solutions. These are the same line. All right, and you can see that by, if you multiply everything here by a minus 2, you would get a minus 2x plus y equals minus 8. They're the same equation. So they are the same line. So this is never true, no solutions. This is always true, all solutions. Okay, or an infinite number of solutions. Okay, we don't need to go into all this stuff for higher level math. We don't care about all that. So let's look at applications. Why would you need to know this for business? All right, well, this happens a whole lot in business, actually. Many real world problems, blah, blah, blah. Let's take an example. Jasmine wants to use milk and orange juice to increase the amount of calcium and vitamin in her daily diet. So there's two things that you want to consider. An ounce of milk, all right, an ounce of milk contains 37 milligrams of calcium, 57 micrograms of vitamin A, and an ounce of orange juice contains 5 milligrams of calcium and 65 micrograms of vitamin A. How many, let me do this in orange. How many ounces of milk and orange juice should Jasmine drink each day to provide exactly blah, 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 blah? So the first thing we know is there's two things that we're trying to find out. How many ounces of milk? How many ounces of orange juice? So the first thing when you do a word problem is you have to decide what your variables represent. Since they're asking specifically how many ounces of milk, that's what we say is X. And then how many ounces of orange juice, that's what we're going to call Y. So the X and the Y, you define them to be whatever the question is asking. Okay. If you define them to be anything else, it's going to make the problem much more difficult. The hardest part of every word problem is defining your variables. Okay. So we got all these lines here. It's not helping me. So how do we set this up? First thing, we define our X and our Y. All right. And now we need some equations. There's two unknowns, so we need two equations. Okay. What do we want? We want 500 milligrams of calcium. Okay. Well, let's see. So let's focus on calcium right now. We have 1 ounce of milk contains 37 milligrams of calcium. So if we take 37 times our ounces of milk, right, that's the calcium from the milk. And now let's look at the calcium from the orange juice. Let's see. And orange juice is 5 milligrams of calcium. So we'd have 5 milligrams times calcium, right? Yeah. So X here is number of ounces in milk. So if we take the calcium from milk and the calcium from orange juice, we need to get exactly 500 milligrams of calcium. So everything here is in milligrams. So 37 ounces, all right? So it's really 37 ounces. And then the X here is X milligrams per ounce. We're talking about calcium. So the ounces go away. So everything here is milligrams. So we're not even going to write the milligrams down. Okay. That's one equation. Now let's focus on the other thing. They want 1200 micrograms of vitamin A. So let's look at the orange juice. Orange juice has 65 micrograms of vitamin A per ounce. So 65 micrograms times the number of ounces of orange juice. And let's look at milk. Okay, milk has 57 micrograms of vitamin A for every ounce. So 57 micrograms times the number of ounces of orange juice. This should have been a Y, I'm sorry, y'all. All right, so this is our milk, our orange juice. All right, 65 micrograms, or 65 micrograms of vitamin A times the number of ounces of milk, 57 micrograms of vitamin A times the number of ounces of orange juice, and they say that needs to be exactly 1200. So there's our two equations. So step one is define your variables. Step two is set up two equations with the information that they give you, okay? And then step three is solve. So the easiest part is actually solving, right? The question tells you exactly what to label these. This is the hard part, right? Now to solve, we could do it by substitution or by elimination. Now, it's hard for me to multiply 5 times something to get 57 or turn a 37 into a 65. So let's do substitution, right? I would have 5y equals 500 minus 37x, or y equals dividing everything by 5. I get that. So these are ugly numbers, right? So I found out what y is in terms of x. I'm going to plug it into that. So we get 65x plus 57 times this pile of stuff. That's what my y here is, right? That's what my y is. And then I get equals 1200. Okay, so now I can solve for x. So multiplying this thing out, 65x, 57 times 100 is 5700. And then whatever this is, I'll use my calculator. I'm not going to turn it into a decimal, okay? Because I want an exact answer. So 57 times 37 is 2109 over 5, and then I have an x equals 1200. And if you're going to plug this into a calculator, do not turn it into a decimal. Don't round off. We want exact answers. So if I have this minus that to combine like terms, I need a common denominator. So if I multiply 65 by 5, this is the same thing as 390 over 5. Okay. So 390 minus 2109. That's going to give me negative 1719 over 5. And now I'll take 5700 and subtract from both sides. So 1200 minus 5700. That gives me negative 4500. Multiply both sides by that. So that tells me that x is the 4500 times 5 is 2500 divided by 1719. All right, at this point, now I'll approximate. This is approximately 13.09. Now I know what x is. I'll plug it in up here. So this is 100 minus 37/5 times 13.09. So let's see here. Negative 13.09 times 37 divided by 5, then add 100. I'm getting approximately 3.134 for my y value. Okay, and of course we'd want to check our work as well. So these real world problems, you're going to get nasty numbers, right? And you want to refrain from using decimals till the very end. At the last step, here's an exact answer, right? And then here's an approximation, right? I really should have plugged in this exact answer here instead of 13.09 to get what my y value is. All right, let's see. Let's check out their solution and see if I was even remotely close to my rounding here. I got 12.5. But let's see. Trying to work too fast. Let's check their work here. I got 13.09. I did something wrong with my arithmetic. It's working too fast. So my equations were right. 37x plus 5y equals 500. 37x plus 5y equals 500. And then 57x plus 65y equals 1200. 57. I got my that's what wrong. It should have been, I got my milk and my orange juice flip-flops in the second one. That's why I got the wrong answer. It's hard to look through this whole paragraph, right? So if you're doing this like for an exam problem, you have to be very careful. I would typically, if I was taking my time to do this, I would draw a chart, right? I'd be like milk, orange juice, right? And then I would say over here, what was it? Calcium and vitamin A, okay? And then I would fill in this chart, all right? So that I don't have to read all these words, okay? So I'd look at this and say, okay, milk, 37 milligrams of calcium, 57 micrograms of vitamin A, then orange juice, uh, 5 milligrams of calcium, 65 milligrams of vitamin A. What's our X and Y? X is milk, and then Y is orange juice. Okay, so you can kind of see from here, it was 37X plus 5Y, right? So this is my X column. These are all going to be the X's, and these are all going to be the Y's, right? So if I just write this chart, it's easier not to mess up. I have 37X, 5Y, 57X, and 65Y. And I didn't fill out the rest of the chart here. And over here, I put N for needed, right? Let's see, we need 500 milligrams of calcium. Here's calcium, I need 500. 1200 of vitamin A, here's vitamin A, I need 1200. So I could put 500 and 1200. If you draw the chart, it makes it a lot easier, right? X, Y, N, and then calcium and vitamin A. So this it's basically just the chart, right? And this is going to be important because later on we're going to be matrices, right? If you have this, if all your equations are in the same order here, you can get rid of all this. You could just write later, we'll just put 37, 5, 57, 65, 500, and 1200. So later on, we're going to throw away all the pluses and the X's and the Y's. We're just going to put a box with the numbers in it because that's what it really is. All right, this is called a matrix. We'll do that at the end of the semester. All right, and it just makes things a whole lot easier. It's one thing when you only have 2 variables, but if you have like 15 variables and 15 equations, you don't want to have X, Y, Z, A, B, and all this stuff. You run out of letters real quick. All right, so typically this stuff is done with matrices. Okay, but once you get your equations written down correctly, right, all they did was substitution here. No, they did it by, yeah, with these, it's easy because I could multiply, I can turn a 5 into a 65 by multiplying everything here by what, 13? If I multiply everything by 13, I get this. Then I could add these, those go away. I get that, and simply divide by 424. Once you got the X, you can plug it in. Okay. My numbers here suck because I got those backwards. But again, this chart will help you not make the mistake that I made. All right, let's look at another example. Look at problem number 6, or match problem here. So we're going to make a chart this time so we don't mess it up. Let's see. Dennis wants to use cottage cheese and yogurt. All right, cottage cheese and yogurt. To increase the amount of protein and calcium. Let's see, this is cheese. Protein, calcium. And over here, how much we need or want or whatever. An ounce of cottage cheese contains 3 grams of protein and 15 milligrams of calcium. An ounce of yogurt contains 1 gram of protein, right? Yogurt, protein, and 41 milligrams of calcium. How many ounces of cottage cheese and yogurt should Denise eat to provide exactly? We want 62 grams of protein, that's what we need, and 760 milligrams of calcium. I'm going to define my X to be, read the question, ounces of cottage cheese. And then Y is ounces of yogurt. Yogurt. So X is cheese and Y is yogurt. I can write down my equations real quick here. It's uh, 3 milligrams of protein times a number of ounces of cheese plus 1 milligram, right, which we are not going to write, times the number of ounces of yogurt should give me 62. So this is my protein, right? And now for calcium, I get 15 milligrams of calcium for every ounce of cheese, and I get 41 milligrams of calcium for every gram of yogurt, and I need a total of 760. So this is my calcium or whatever, calcium. All right, so there's my equations. Okay, so I'm going to multiply this thing by a -5. I'll keep this dude. I'll keep this one. All right, but if I multiply everything here by a -5, I get this, this, and then whatever 62 times -5 is. 62, 310. If I add these, those are going to go away. 41 minus 5 is -36. 760 minus 310, 450. Adding those. This is positive, isn't it? Yeah. 41 minus 5. There we go. So 450 divided by 36 is 12.5. Now that I know what y is, I can plug it into either equation. It doesn't matter. If I plug it into this one, I have 3x plus 12.5 equals 62, or 3x equals, let's see, subtracting 12.5 from both sides, I got that. And then dividing both sides by 3, I get 16.5. So you see here, this isn't a whole lot of work. That's everything, right? I'll plug that in here, and I get that. Okay. Kind of hard to show your work with stuff. You have arrows and stuff going everywhere, right? The book has their mode, right? This looks nice the way they laid it out, right? So if you're going to do this for an exam or a quiz, you're going to want it to look more like the way they did it here, okay? You want it to be as organized as you can. Get it. That way if somebody's reading your work, they need to be able to follow it, okay? This isn't exactly that easy to follow. It kind of is. You know, it's not too bad, right? I would have to do like that, and I would say, let's see what I did. I multiplied by a -5. Okay. So that's how you do it. Substitution, or this is a elimination here. Right? Elimination in this case was easier because it was really easy to turn a 3 into a -15 by multiplying everything by a -5. Problem number 6. Oh, this equilibrium stuff. All right, let's go back to the beginning of their paragraph here. Here we go. In the free market, so we're gonna begin this, and then we're gonna study this up, and the next time we're gonna restudy it, and then work some problems for this equilibrium stuff. This is the hard part, right? The actual business. Let's get the rest of our paragraph here. Remember the last section, it ended with equilibrium. So in a free market economy, the price of a product is determined by the relationship between supply and demand. All right. So price depends on both supply and demand. Suppliers are more willing to supply a product at a higher price. So when price is high, supply is high. That makes sense now. Remember that on the last class, at the end of the class, I was like, why is it when the supply is going up, the price is going up? I thought the price went down right? If there's a whole lot of it, shouldn't the price go down? I was looking at it backwards, so this is explaining it. It's the dependent is going the other way. I was thinking high supply means low price. But no, if you think about it the other way around, if the price is high, suppliers are more willing to supply. Okay, so I was looking at the dependency backwards. All right, if the relationship between price and supply is linear, then the graph of the price supply equation is a line with positive slope. Okay, that's what we had last time. Let me pull that up. This guy is what we did last time, right? This was the quantity, supply or demand, and I was looking at, and here's the price. I was looking at this going, well, if the supply is going up, why is the price going down? Like they said, read it the other way around, right? The higher the price, the more people are willing to supply. All right, so interpreting like that, it makes sense. Okay, on the other hand, consumers of a product are generally less willing to buy a product at higher prices. So when a price is high, the demand is low. Okay, that makes sense. And I was reading this one backwards, right? For the demand, I was like, well, the higher the demand, shouldn't the price be going up? But no, it goes down in this graph. Okay, because I was thinking, I started here and said, well, what does it do to that? No, think about it the other way around, right? If the price goes down, the demand will go up, right? Lower price, higher demand. Okay, so we can graph both of these. We have let's see, the demand depending on the price and the supply depending on the price. If these are linear, they're both lines. We want to know where they intersect, and that's just exactly what we've been doing in this section. The last section, we graphed this and we just looked at it and said that's where they cross, right? So we could figure out the equilibrium price. Now we know how to actually do it mathematically instead of just looking at the graph. All right, once we find where these lines cross, that tells us the equilibrium price and the equilibrium quantity, right? So I looked at this and was like, well, in one equation, X was supply, and the other equation, X was demand. Either way, this is a quantity. This is the number of skateboards or whatever the hell they're selling, okay? So next time we will do these, example 7 is where we'll pick up. So what I want y'all to do now is your exam for the day. So this is daily, dang it, daily exam number 6. All right. Solve the system. Okay, so number 1, I'm going to have x plus y equals 1 and 2x minus y equals 2. So you can do it via substitution or elimination, whichever way you want. 2x plus y equals 2 and 3x minus 2y equals 4. All right, there's your exam. All right, substitution or elimination, whichever way you want. Okay, there should be one unique solution, I'm pretty sure. All right, it's possible these could be parallel, I don't know. So there's either one solution, no solutions, or an infinite number if they are the same line. And that's it for today, folks. Thank you for your patience. Make sure you don't have any missing exams or quizzes. All right, get them in for at least half credit. The solutions are there in Canvas, so you have no excuses. And tomorrow afternoon, I'll turn in progress reports for y'all. All right. All right. Be safe, stay warm, and I will see y'all on Tuesday.
Thank you too.